Good morning to all of you.
Good morning, sir.
Good morning. Good morning. So, are there any questions, doubts? Anybody, any question, doubt on whatever we discussed yesterday's class or otherwise? Okay, so if there are no questions, let me start. So we are continuing with the finite deformation. So last class I introduced you green Lagrange strain tensor, which is used with a Lagrangian description of motion, and I also introduced Eulerian-Almansi strain tensor, defining the Eulerian description of motion. Although we don't use that, but yeah, I have defined that. So we are continuing with that. So today I will be talking about relationship between the differential volume in the reference and the current configuration, and similarly the relationship between the area in reference and current configurations, and then these different stress measures. Okay, it is not writing, so let me. Is the screen visible?
Yes, it's visible.
Okay. Yeah, so I'm going to continue with finite deformation. So yeah, so I will first discuss the volume ratio. So for that, let us say that now we have the reference frame and the coordinate system embedded in that. So the coordinates for undeformed configuration are capital X size, and for the deformed configuration is small x size. And say the unit vectors are E1 cap along this direction, then we have x2, small x2 and E2 cap, and we have x3, small x3 and E3 cap. So E1 cap, E2 cap, E3 cap are unit vectors. So E1 cap, E2 cap are unit vectors along x1, x2 and x3 directions. So now what we want to do is we want to find out this ratio dVt by dV naught. This ratio we want to find out. So for this we consider let us say a differential volume element in the reference configuration is a cube, cuboid, not cube, cuboid. So this is the differential element, and this edge is parallel to x1 axis, so this is dx1, this is dx2, and this is dx3. And the volume of this cuboid is dV naught. This is in reference configuration at t equal to 0. And then this gets transformed to the current configuration, so it will become a parallelepiped. it becomes a parallelopipe. So in that case, this is, let us say this is dl1 cap is a vector, this is dl2 cap, as a vector dl1, vector dl1, vector dl2, and this is vector dl3. And the volume of this parallelopipe is dvt, and this is in the current configuration. At any time t. So now if you look at dv naught, because in the reference configuration we have a basically cuboid, so for that the volume is dv naught is simply going to be dx1 into dx2 into dx3. So this is the volume in the reference configuration of the cuboid, and in the deformed configuration, current configuration, that volume can be written as a scalar triple product. So we have vector dl1 dot vector dl2 cross vector dl3. So that will give you the current volume. Now we want to write these vectors dl1. So initially the line along dl1 cap was parallel to x1 axis. So there is a change because of change in capital X1. There is a change in small x1, x2, and x3 coordinates. So therefore the vector dl1 can be written as del x1 upon del x1 into dx1. This will be along this change is going to be along E1 cap direction. So let me put that, and plus you will have along x2 rate of change of x2 with respect to x1 into dx1. This change would be along the unit vector E2 cap, and plus we will have del x3 upon del capital X1 into dx1 into E3 cap. So this is going to be a dl1 vector dl1. That is this vector dl1. What is this line was initially in the reference configuration is parallel to x1 axis, and then it becomes oriented in x1, x2, and x3 space. So the component this vector dl1 is given by this rate of change of x1 with respect to capital X1, rate of change of small x2 with respect to capital X1, rate of change of small x3 with respect to capital X1, gives you the component along E1 cap, E2 cap, and E3 cap. So similarly, you can write vector dl2 cap del x1. Now this initially this this line element is this line element is parallel to x2 axis. So there is change in x2 capital X2 coordinates. So rate of change with respect to x2 into dx2 E1 cap plus del x2 by del x2 into dx2 into E2 cap plus del x3 upon del x2 into dx2 into E3 cap. So you can write the this dl1, dl2, and dl3 vectors like this. So similarly, dl3 will be equal to del x1 upon del x3 into dx3 E1 cap plus del x2 upon del x3 dx3 into E2 cap plus del x3 upon del x3 into dx3 into E3 cap. So these are the unit vectors. Now if you look at the dot product, so as I said, dvt, the differential volume in the deformed configuration is dl1 dot dl2 cross dl3. So this can be written as determinant of 3 by 3 in the first row, in the third row. So you can write this as del x1 upon del x1 into dx1, del x2 upon del x1 into dx1, del x3 upon del x1 into dx1, then del x1 upon del x2 into dx2, del x2 upon del x2 into dx2, capital X here. So please keep in mind that this is capital X2, and then del x3 upon del x2 into dx2. And the last row will be the components of dl3 vector, that is del x1 upon del x3 into d del x3 into dx3. So yeah, this is what you can write. So now you have this as the dvt. So you would see that dvt can be written as now in the first row we can take dx1 common, second row we can take dx2 common, and third row we can take dx3 common. So you will have dx1 into dx2 into dx3 as a common term, and inside you will have this 3 by 3 determinant, which would be del x1 by del x1, del x2 by del x1, del x3 by del x1, and then del x1 by del x2, del x2 by del x capital X2, del x3 by del x2, and then del x1 by del x3, del x2 by del x3, del x3 by del x3 into dx1, dx2, dx3. That is taken out of the determinant. So you get this. Now you will see from this that dvt is equal to, now if you look at this is nothing but, if you remember, it is the determinant of F transpose. If you look at this determinant, so this is actually the determinant of F transpose. So determinant of F transpose and dx1 into dx2 into dx3 is dv naught. So you have this ratio. So you can determinant of F transpose would be same as the determinant of actually F. So we can also write this as F into dv naught. And determinant of F, let me denote it by J. So we can say that this ratio dvt by dv naught will be actually equal to A is determinant of F is equal to determinant of F transpose. So this is the volume ratio. So if you have a differential volume in the reference configuration, that translates into a differential volume in the current configuration. So the ratio of these two volumes is equal to determinant of the deformation gradient matrix F. That is J equal to F. Determinant of F is equal to determinant of F transpose. So if we have the mass conservation, so if you look at the mass conservation, so mass conservation means the volume mass of the differential element in the reference configuration will be same as mass of the same element in the current configuration. So dm naught would be equal to dmt, and dm naught we can write it as rho naught into dv naught and is equal to rho t into dvt. Rho naught is the density in the reference configuration, density of the material, and rho t is the density of material in the current configuration. So from this relation you can write the ratio of density in the current configuration to density in the reference configuration will actually be dv naught by dvt, and which is 1 upon j. So this is another relationship between the densities in the current configuration and density in the reference configuration. So we have this relationship, and another relationship is this volume ratio in the current and reference configurations is given by this J, determinant of the deformation gradient matrix. There is another relationship between the areas, because we need these concepts in the formulation, so that is why I am discussing. So the another important relationship is known as the Nessels. Yeah.
Sir, like
yes.
Hello, sir. Am I audible? Hello.
Yeah, so some echo is coming, but anyway, please tell.
Yes, sir. So actually, I wanted to ask, like in the reference configuration, why don't we take it as a why we take it as a cube, not as a, we took in the current configuration? Means why we take the three edges which are aligned with the axis in the reference configuration?
Why do we not take what?
Sir, in the current configuration, we are taking it as a parallelepiped.
Yeah.
But why not in the reference configuration we are taking it as a parallelepiped?
No, in the reference configuration, we are taking it as a basically cuboid, so that we can easily write. You can, it's a choice is with us. So why we are taking cuboid, so that we can easily write the basically this volume of that. So if it is a cuboid, since simply the volume is dx1 into dx2 into dx3, so we are taking edges parallel to coordinate axes x1, x2, and x3 in the reference configuration, and then that deforms to a parallelepiped. So if we take parallelepiped in the reference configuration itself, so then you have to specify in which direction those edges are, and then we have to the expression for volume will also be complicated. So we can easily, and it is general enough that we take a cuboidal element in the reference configuration, and that translates to a parallelepiped, and we can easily relate the these differential volume ratios. So we can always take any differential volume in that manner.
Okay. So how we know it is general, sir?
It's general because we are talking of a differential volume. So we are taking a differential volume, and then we are trying to write because differential volume is the edges are infinitesimally small. So that is why I am saying that it is general.
Okay, sir.
So another relationship is in terms of area in the current and reference configuration. So that is known as the Nasson's relation. So in this also what we are doing is a slightly different approach, because we want to emphasize the area, arbitrary area with unit normal specified. So let us say again we have this coordinate axes. So same, you have x1 small x1 and e1 cap, x2 small x2 and e2 cap, and x3 small x3 and e3 cap. And then in the reference configuration, if we take our area, let us say we take this differential area. So area is dA, differential area, and the unit normal to this is in this direction. So this vector is, let us say, n cap. And around this volume, we consider around this area, based on this area, we consider a general volume like this. And so now if we look at this edge, one is area dA and normal n cap, and let us say this normal to the area n cap is having components n1 e1 cap plus n2 e2 cap plus n3 e3 cap. So these are the unit normal to the area, and dA is the magnitude of the area, and this volume what I am considering. So let us say this vector, this is d vector dl, and that is now a general one, that dl1 into e1 cap plus dl2 into e2 cap plus dl3 into e3 cap. This is in the reference configuration. That is at t equal to 0. And then in the current configuration, when we look at, so this area translates to this different let us say this area now becomes a small dA in the current configuration. The normal to the area is small n cap, which is given by n1 e1 cap plus n2 e2 cap plus n3 into e3 cap. And then around that I consider a volume. So that volume is also with this edge is, let us say, is d small l, with the components dl1 dl2 dl3 along e1 cap e2 cap and e3 cap directions. So this dl is equal to dl1 into e1 cap plus dl2 into e2 cap plus dl3 into e3 cap, and this is the current configuration at any time t. So now we want to, in this case, we want to find out the relationship between the area in the reference configuration and area in the current configuration. So area as a vector when we write, so dA, in the capital A denotes the area in the reference configuration. So dA will be equal to its normal and component of normal n1, n2, n3 into magnitude of area is capital D capital A, and the area vector in the current configuration with its normal along small n1, n2 and n3 into magnitude of the area is d into small a, d small a. So now we look at the volumes. Now although earlier we have derived the volume ratio basically in terms of cuboid in the reference configuration translating to parallelepiped in the current configuration, but here also we can have the same relationship between those volumes, the another differential volume. So if you look at this volume is dv naught and this volume is dvt. So these know the area, know the volume dv naught will be equal to, again you can write the dot product of area vector and dl vector. So dot product can be written as vector if I write in this form. So dl transpose into n dA, this will be the volume in the reference configuration dv naught, dl transpose n dA is dot product of vector dl and vector d capital A. And similarly the volume in the current configuration will be given by d into small l transpose into this vector small n, which is having component small n1, small n2, small n3, d into small a. Now if you look at this dl, the relationship between dl and capital DL, so this components of dl will be, so the dl is component of dl are in the current configuration. So the way we derived the relationship between, if you remember, we have written the relationship between d small x1, d small x2, d small x3. So this relationship is same. So we can write this d small l as deformation gradient into d capital L. And the ratio between the volumes, we have this dvt will be equal to, we have already derived that this is j into dv naught, where j is the determinant of deformation gradient matrix. So then if you look at, we can write this relationship. So we can write now dvt is dl transpose into n into dA. So this is already equal to j into dv naught. So we have j and dv naught is dl transpose into n into d capital A. So this we already know. Now in this using this relationship, we can write dl transpose as this capital dl transpose into f transpose into n dA will be equal to the other side we have j into dl transpose into n into d capital A. So we can write this relationship. This is straightforward. And now if you what we can actually do is we can take the term on the right hand side to the left hand side, and we can take dl transpose as a common. So if I take the dl transpose as a common, so what I will have is actually this f trans, not the f is a matrix. So we have f transpose into n dA minus we will have j into n into d capital A. This is equal to 0. So now dl is arbitrary. We can choose dl d capital L arbitrarily. So for this product to be 0, that means this term has to be 0. So that is this implies then that F transpose into N dA is equal to J into NDA. Or if you want to write the reference area, that is the NDA vector in the reference configuration, NDA will be equal to 1 upon J into F transpose into NDA. So this relationship is known as Nelson's relationship, that as I have written. So this is the final relationship between the area vector in the reference configuration and area vector in the current configuration. So component of normal to the area are capital N1, capital N2, capital N3 in the reference configuration and small n1, n2, n3 in the current configuration. So this is the another important relationship we use. Now let me introduce the different stress measures. So I will briefly explain. So now I am going to talk about the stress measures. So again, for the purpose of demonstrating this.
Hello, sir.
Yeah.
So that volume, how did you write that? DL into NDA, that can you help us? DL transpose NDA.
So this is actually, I have written as the dot product. So when you are writing, if you take the dot product of this area vector and the vector L, so essentially, if you take the component of D for this differential area, if you take the component of DL along the normal to the area, that will give you the volume. So essentially, I have written this as the dot product of vector DL and vector DA. So what is written over here is the dot product of, so if you take area and length, the component of DL along normal to the area, that gives you volume. So that is how I have written these two. It's a dot product basically between the area vector and the DL vector.
Okay, so then how is like DL defined? That can you tell?
DL is arbitrary vector. No, I have just said over here that DL has got component along x1, x2, and x3. So DL1, DL2, DL3, these as you see. Similarly, for this D small l, you have components along DL small l1, D small l2, D small l3 along E1, E2, E3 direction. So this is in the reference configuration, and that gets transformed to this in the current configuration. So the area gets transformed to this area with a different normal, and vector D capital L gets transformed to vector D small l. As you see over here.
Okay, so volume can be written like that. DL dot.
Yeah, volume can be written as dot product of area vector and this DL vector. So essentially, you are taking area into component of this height along the normal. So area into height along normal gives you the volume.
Okay.
Yes. Measures. So again, we have these reference and current coordinates. And now let us say we have some plane, and in that there is a let us say this area in the reference configuration is NDA. So magnitude of area is DA. This is again reference configuration, that is at t equal to 0, and then this gets translated to another if the same area, if you look at, this gets translated to another area. This is vector n and then small da. And in the deformed configuration, actually in any deformable body, when you apply the load, it deforms. So actually finally load acts in the deformed body. So let us say there is a differential force vector df is acting in this. So let us say that force vector is actually traction. So this is acting in the area, the deformed area. So this is the current configuration at t, and df, what I have written, this vector df, this is the force acting on area NDA in the current configuration. So now you have now if you look at the different stress definition. So Cauchy stress is basically when you define the traction based on Cauchy stress. So that is the force per unit deformed area, force in the current configuration per unit current area. So based on the Cauchy stress, so if I use Cauchy stress, so then in that I can write this vector df, that force is equal to this is Cauchy stress tensor sigma into NDA. So it is defined, the Cauchy stress is defined as force in the current configuration per unit current area. So you can think of something like that. So that is how the Cauchy stress is defined. This sigma is Cauchy stress, what I have written over here. And then we have another definition which is known as the first Kirchhoff stress tensor. So in this one, you look at the first Kirchhoff stress is defined as force in the force in the current configuration per unit original area in the reference configuration. So that is why when you write this df, so df based on the first Kirchhoff stress, let us say, is denoted by capital P. So this would be capital NDA. So you would see here capital P is like df upon NDA. df is the force in the current configuration, and NDA is the area is the area in the reference configuration. So based on this, we define the first Kirchhoff stress tensor as force in the current configuration per unit area in the reference configuration. And then we have what is known as the second Kirchhoff stress tensor. Second Kirchhoff stress. In this, what we do is we define this force df. The force I have over a differential area NDA is actually transformed, pulled back to the reference configuration. So let us say that pulled back force is df naught in the now reference configuration will be equal to the notation I'm using for second Kirchhoff stress as capital S and into capital NDA, area in the NDA. So you can see that roughly, loosely speaking, we can say the second Kirchhoff stress tensor is force in the reference configuration per unit reference area in the reference configuration. So we have these three relations. df is equal to sigma NDA, small NDA, and df is equal to capital P, capital NDA, and df naught is equal to capital S NDA. So these three relations we have based on the Cauchy stress, first Kirchhoff stress tensor, and second Kirchhoff stress tensor. Now sir, here, yeah.
Sir, the force vector have only three components, like in x direction, y direction, and z direction. And the stress, right, for the stress should be 3 cross 3. So only we are taking the plane stress or plane strain condition, or
no, we are taking the 3 by 3 only, but it is the multiplication. So that is how I'm writing df as sigma into NDA, no? So sigma is here 3 by 3 matrix, and n is a 3 by 1 vector. So the multiplication will give you a 3 by 1 vector.
Okay.
So here, this, yeah.
Sir, can you define that df not only I was asking? Yes,
pardon, say again.
Yes, sir, df not I was asking. What is df?
Yeah, df is the force vector in that basically over this small area NDA in the current configuration. So you see this area is NDA, and in this there is a force which will have component along x1, x2, x3 directions, that is given by vector df.
df
so pardon? Yeah,
df
naught I'm going to define. So I'm going to write that. So df naught is the force vector refer to reference configuration. So kind of we use against transformation based on the deformation gradient matrix and write this df naught. So df naught is related to actually df through the deformation gradient, because now if you look at I have, so I can write df naught. Now df naught is the force in the reference configuration. So we have defined the inverse deformation gradient. So we can relate this df naught to df using the inverse deformation gradient. So we assume that df is pulled back to the reference configuration through this inverse deformation gradient tensor. So df naught, vector df naught can be written as del capital X1 upon del small x1, del capital X1 upon del small x2. मेरी क्लास है ना, क्लास है अभी, क्लास चल रही है. Yeah, sorry. So I can use the inverse deformation gradient to relate the force in the refer to reference configuration in terms of force in the current configuration. So the force actually is acting in the current configuration, but we are referring it to the reference configuration and relating this to the force in the current configuration through this inverse deformation gradient. So we can write, assume that it translates exactly like differential elements in the reference and current configurations. So del x1 upon del x3, and then you have del x2 upon del x1, del x2 upon del small x2, del x2 upon del small x3, and del x3 upon del small x1, del x3 upon del small x2, del x3 upon del small x3. This into df. So this is the actually we are assuming that the force in the current configuration can be pulled back to the reference configuration through this inverse deformation gradient matrix. So that is this is G into df.
Hello, sir.
Yeah.
Sir, can you tell the physics behind that df naught?
So yeah, we are physics is essentially, see, as I said, actually the force acts in the current configuration actually. So because the reference configuration there is no load, no stress, and in the current configuration there is a stress and there is a corresponding force in this differential area. Now we want to represent this by an equivalent force in the reference configuration. So df naught is a mathematical concept which is basically the force df in the current configuration refer to the or you can say kind of an equivalent force in the reference configuration. So df naught is the equivalent force in the reference configuration. So that is how you can actually think of it. And the relationship between this force df and the force here df naught is through the inverse deformation gradient. So that because we are trying to relate the some quantity in the reference configuration in terms of quantity in the current configuration. So if you remember, we had related the differential element in the reference configuration in terms of differential element in the current configuration through inverse deformation gradient. So we are making use of the same relationship. So you can say df naught is an equivalent force in reference configuration.
Okay, sir. And why it is required, like for defining second Piola-Kirchhoff stress?
Yeah, it is required for defining the second Piola-Kirchhoff stress tensor. Yes.
Okay.
So as per the concept of second Piola-Kirchhoff stress tensor, we want equivalent force in the reference configuration, and we want the area in the reference configuration, both in the reference configuration, and that is why we are doing this. So now G is equal to F inverse. So we have said that this D, then df naught is nothing but actually F inverse into this df. So now this is as per the definition I have told. Now we want to relate the different stress measures, Cauchy stress, first PL Kirchhoff stress, and second PL Kirchhoff stress tensor. So let's look at the relationship between them. So let us say the relation between Cauchy stress sigma and first PL Kirchhoff stress P. So we want to relate these two tensors. So now our starting point is this force df. So we know that df in terms of Cauchy stress tensor is written as sigma into current area in dA, and this same can be written as the same df we use for defining the first PL of Kirchhoff stress tensor. So this same df can be written as actually P into NdA, and we have derived the Nelson's relation. So we can say that sigma into NdA is equal to this P we have, and then we have derived this NdA is equal to 1 upon J into F transpose NdA. So we have P, and then NdA is 1 upon J into F transpose into small n dA. This relationship we have derived. No, I am referring to this relationship. What you have over here, capital N dA is equal to 1 upon J of transpose N dA. So I am writing this as P into 1 upon J of transpose N dA, and then now you can see that we can write now the sigma NdA is common, small NdA here, and small NdA is common here. So from this you can say that Cauchy stress sigma is equal to 1 upon J times P into F transpose. So this is the Cauchy stress in terms of first PL Kirchhoff stress tensor. And you can write the inverse relationship also. So you can write P. So P equal to, if you post multiply by F inverse transpose, you can get P in terms of sigma. So you can see from this relation, you can also write P equal to determinant of the deformation gradient, that is J into sigma into F inverse transpose. So this is the relationship between Cauchy stress and first PL Kirchhoff stress tensor.
For the first PL Kirchhoff stress, is the stress in the current configuration? No?
No, yeah, first PL Kirchhoff stress actually is the force in the current configuration per unit area in the reference configuration.
So the stress is in the current configuration or in the reference configuration? The stress.
Yeah, force is in the current configuration, but the area taken is in the reference configuration.
Reference configuration.
Yeah.
So the stress will.
Yeah. Now the stress is, yeah, you see, Cauchy stress is of course the stress acting in the reference current configuration. First PL Kirchhoff, we can say kind of stress acting in the reference configuration. Because we are taking the current force divided by reference area. So it is kind of force per unit reference area.
The second PL of Kirchhoff stress even the reference configuration.
Yeah, the force is also taken in the reference configuration. And the area is also taken
in the reference configuration.
Yeah. Okay. So now similarly, let us derive the. Now you would actually see sigma for non-polar materials, solids. Sigma is a symmetric stress tensor, as you know. Know from your continuum mechanics concepts that sigma ij equal to sigma ji. So sigma is a symmetric tensor, but when she be multiplied with P into F transpose. So now this P equal to J into sigma into F inverse transpose. So P will be unsymmetric. even though sigma is symmetric, but P would be unsymmetric because F is not a symmetric matrix. We are multiplying F inverse transpose, so P will become unsymmetric. So that is even for non-polar materials, first P of Kirchhoff's stress tensor is going to be unsymmetric tensor. Now let us look at the relation between sigma, that is Cauchy stress, and the second P of Kirchhoff's stress tensor. So again, our starting point is that we know based on the Cauchy stress, the force vector in the current configuration is given as Cauchy stress sigma into NdA, and based on the second P of Kirchhoff's stress, we know that dF naught is given by second P of Kirchhoff's stress tensor into NdA. So now if you look at, we have already seen that dF naught is equal to F inverse into dF. We have seen this relationship, and this is equal to S into N into dA. And now we can write this dF in terms of Cauchy stress, because we want to relate second P of Kirchhoff stress and the Cauchy stress. So we can write this S into N dA is equal to F inverse is already there, and then your dF is sigma in terms of Cauchy stress, sigma into small and d small a. So you can write it like this. Now NdA, we using the Nasson's relation, we can write this capital NdA as 1 upon j into F transpose into NdA will be equal to, this side we have F inverse into sigma into NdA. And now you see small NdA is common on both the sides. So you can now express, let us say, if you can say that S 1 upon j into F transpose is equal to, other side we have this Cauchy stress. Now if you pre-multiply by F, so if you pre-multiply by F in this equation, you can write sigma is equal to F transpose, 1 upon j will be there, so 1 upon j F transpose, not F transpose, but F, so 1 upon j F into S into F transpose. So this is the relationship between the Cauchy stress sigma and the second P of Kirchhoff stress tensor S. So sigma is equal to 1 upon j F into S into F transpose. And similarly, now so this is one relationship you get over here. And the other relationship now you can express if you basically post multiply by F inverse transpose on both the sides. So you will get S, and S will be equal to J into, you will have F inverse into sigma into F inverse transpose. So you get this as the another relationship. So you will see sigma is symmetric, Cauchy stress is symmetric, and we are multiplying by F inverse, pre-multiplying by F inverse and post-multiplying by F inverse transpose. So S will be actually symmetric. So the advantage with the second P of Kirchhoff stress tensor is that it is referred to reference configuration and it is a symmetric tensor. Whereas the first P of Kirchhoff stress tensor is kind of hybrid based on current area in the force in the current configuration and area of the reference configuration. It is also unsymmetric. Whereas second P of Kirchhoff stress tensor is actually symmetric. So now similarly, you can derive the relationship between S and P. So if you want to derive the relation between S and P, so we have already seen that P is nothing but J into sigma into F. In this relationship we have seen here. Yeah, P equal to P you can say is equal to J into sigma into F inverse transpose. So P equal to J into sigma into F inverse transpose. So you can say this as P into J, and then we know sigma in terms of S. So that is 1 upon J into we have F into S into we have this F transpose, and then finally know this F inverse transpose. So you can say that this P will be equal to F into S. Or if you want to write S, you can say S is going to be F inverse into P. So these are the relationship between these three. Are no different relationship between Cauchy stress, first Piola-Kirchhoff stress tensor and second Piola-Kirchhoff stress tensor. So these are the relations, and major role is played by deformation gradient F. And now if the displacement gradients are small, that is the elements of F are du by del u1 by del x1 and so on. If they are small, so F will be close to identity matrix, and then you will see, and J would be equal to almost unity. So you will see that all stresses would be same. The Cauchy stress of first Piola-Kirchhoff stress tensor and second Piola-Kirchhoff stress tensor, all of them will be same if the deformation gradient, the displacement gradients are small. So now, after having defined strain measures and different stress measures, now let us come to the we ultimately want to develop the element level governing equations. So we need let me start from the big form. So and first I will write the big form in current configuration. So that's more logical, although we can directly start from the principle of virtual work. That's more general, of course, but we need to look at how the different reference and current configurations are coming into picture. So I'm starting with weak form. So you would have derived the stress equations of equilibrium. So in terms of Cauchy stress components, so then the equilibrium is actually studied in the deformed configuration or the current configuration. So the stress equations of equilibrium in current configuration. So we know that, I think this, let me write in the expanded form. So del sigma 1 upon del x1 plus del sigma 2 upon del x2 plus del sigma 3 upon del x3 plus body force in the current configuration FB1 is equal to 0. I am considering equilibrium problem. So these equations I am presuming that so these equilibrium equations are written for the current configuration in terms of Cauchy stress. So we have del sigma 12 upon del x1 plus del sigma 22 upon del x2 plus del sigma 32 upon del x3 plus FB2 equal to 0. So now, and the third equilibrium equation is del sigma 13 upon del x1 plus del 23 upon del x2 plus del sigma 33 upon del x3 plus fb3 is equal to 0. So these are the equilibrium equations. Now we write the weighted residual statement. Weighted residual statement. So we can write that integration, and I am writing this in the current configuration. So the integration over the current volume Vt, and then we will have the all the equations have to come here. So I will write just few terms. So we'll have del sigma 11 upon del x1 plus del sigma 21 upon del x2 plus del sigma 31 upon del x3 plus fb1 into delta u1, the virtual displacement along the x1 direction. Plus, like that, you will have the other two equations here, del sigma 12 upon del x1 plus del sigma 22 upon del x2 plus del sigma 32 upon del x3 plus FB2 into delta U2. So this is weighted residual statement. Plus you will have del sigma 1,3 upon del x1 plus del sigma 2,3 upon del x2 plus del sigma 3,3 upon del x3 plus FD3 into delta U3 virtual displacement along x3 direction into dVt, that is integration over the current volume, so that is dVt is equal to 0. So this is what you get as the weighted residual statement, and this is written in the current configuration, and in the current configuration we are writing this equilibrium equation in terms of Cauchy stress. So that is logical. And then now we come to the big form of this. So now to arrive at the big form, you have to use what is known as the Green-Gauss theorem. So as per this, now we will translate these volume integrals into actually the surface integral, and the derivatives would be transferred from the sigma to virtual displacements delta U1, delta U2, and delta U3. So you will be able to write this relationship, the weighted residual statement, as integration over the current surface area, and into the terms which we will have is sigma 1,1 into N1 plus sigma 2,1 into N2 plus sigma 3,1 into N3 into delta U1, plus we will have the other term sigma. These are coming from the application of the Green-Gauss theorem. So while transferring the derivatives from sigma to this delta Ui's, we want to transfer the derivatives from sigma to delta Ui's. So in the process of that, we use the integration by parts, and in the integration by parts, we generate two type of terms. One is the volume integral, and other is the area integral. So in the area integral, you have finally the traction components coming into picture. So this is this is delta U1, and then sigma 1,2 into N1 plus sigma 2,2 into N2 plus sigma 3,2 into N3 into here you will have delta U2, plus we will have the sigma 1,3 into N1 plus sigma 2,3 into N2 plus sigma 3,3 into N3 into delta U3. So this is the into ds. This term is going over there. So this is this first set of terms, and then you get second set of terms where you have volume integral. So integral over volume Vt. This is St, the current area. So this is the other set of terms from the integration by parts we get is sigma 1,1 into delta of del U1 upon del x1 plus sigma 2,1 delta of del U1 upon del x2 plus sigma 3,1 into delta of del U1 upon del x3. So we get this term. Plus similarly we get other terms sigma, so it is little lengthy, del U2 upon del x1 plus sigma 2,2 into del U2 upon del x2 plus sigma 3,2 into delta of del U2 upon del x3, plus we will have this sigma 1,3 into delta of del U3 upon del x1 plus sigma 2,3 delta. The delta is a variational operator, so as you know it is denoting the virtual displacement, delta of del U3 upon del x2 plus sigma 3,3 into delta of del U3 upon del x3 into dVt. Here you have this dVt. So let me write as a smaller bracket into dVt, and then plus you have this body force term. So we'll have integration over current volume, that is delta U1, delta U2, delta U3 transpose into FB1, FB2, FB3 dVt. This is equal to 0. So this is the big form. And what we can do is multiply the whole thing by a minus sign. And then if you look at this, I'm going to denote as this term as delta epsilon 1, and this I'm going to denote as delta epsilon 2, this as delta epsilon 3, and sigma 1, 2 equal to sigma 2, 1. So I can write sum of these two terms as twice of delta epsilon 1, 2, and so on. So what you can actually do, so yeah, so have you followed this? So we are from the weighted residual statement using Green-Gauss theorem, we are writing this the weighted big form, and this big form can be written as, so multiply the whole thing by a minus sign, and then you can write this big form as Vt, and then you have this delta of epsilon transpose. I'm going to define that into sigma. I'm using the void notation to write this. So we will have dv minus integration over volume, and then you have this body force term delta u1, delta u2, delta u3 transpose into fb1, fb2 into fb3 dv. And then you have the traction, so the integration over the current surface. So you'll have delta u1, delta u2, delta u3 transpose, and into you have these tn1, let me use the small t, later I will use the capital T for the reference configuration. So tn1, tn2, tn3 ds t, this is dvt is equal to 0. So this is the finally you have got this weak form in the current configuration in terms of Cauchy stress. So now where if you look at the various quantities, so let me define and then I will stop over here. So delta of epsilon is actually defined as delta epsilon 1, delta epsilon 2, delta epsilon 3, and twice of delta epsilon 1, 2, twice of delta epsilon 2, 3, twice of delta epsilon 3, 1. And this is actually equal to, in terms of displacements, you can write this will be delta of del u1 upon del x1, delta of del u2 upon del x2, delta of del u3 upon del x3, and then delta of del u1 upon del x2 plus del u2 upon del x1, delta of del u2 upon del x3 plus delta of del u3 upon del x2, and last term here will be delta of del u1 upon del x3 plus del u3 upon del x1. So these are your various basically the components of delta epsilon. So you would see that in this configuration, in the current configuration, in the big form, we get we are not getting either the neither the Green Lagrange strain tensor nor the Eulerian-Almansi strain tensor, but we are getting the these terms, linear terms over here, and this is exact as it is coming from the weighted residual statement and then the big form. So this is what is coming over here, and similarly now sigma, as per the void notation, I am writing as sigma 1, sigma 2, sigma 3, sigma 1, 2, sigma 2, 3, and sigma 3, 1. And the components of traction vector, so Tn1 is equal to sigma 1 into n1 plus sigma 2 into n2 plus sigma 3 into n3, and Tn2 is equal to sigma 1,2 into N1 plus sigma 2,2 into N2 plus sigma 3,2 into N3, and Tn3 is equal to sigma 1,3 into N1 plus sigma 2,3 into N2 plus sigma 3,3 into N3. So you can write it like this. Yeah. So now you have got this as the weak form. So now we want to look at, now we want to write the first term. If you look at over here, first term is actually virtual work of stresses. So if you look at this term alone, this is virtual work of stresses, and we want to write this in terms of various stress measures, particularly the first Patel-Kirchhoff stress tensor and second Patel-Kirchhoff stress tensor and corresponding strain measures. So we want to write it like this. So I will consider this separately. So if you consider the virtual work of stresses from this big form, only that term, virtual work of stresses. So let me denote that by delta W sigma, and sigma is, although I'm using sigma and sigma notation is used for Cauchy stress, but it is denoting a general thing that I'm going to use the same notation for different stress measures. So this is the integration over current volume, and then you have delta of epsilon transpose into sigma into dVt. And we can now see the the current area in terms of the reference area. So we know dVt equal to J into dV naught. So we can write this integral in the reference configuration. The other things we have to see into sigma, and this will be then J into dV naught. So you can write it like this. Now I want to make use of a notation. So this delta epsilon transpose into sigma, whatever we have, we can also write it in terms of the 3x3 stress matrix and 3x3 displacement grade variation of displacement gradient matrix. So now if I consider sigma 3x3 stress matrix into this delta of H, where this is the displacement gradient in the current configuration. Sigma is of course sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, and sigma 31, sigma 32, sigma 33. In 2, I am going to write, yeah, that's a bigger matrix, so I need more space. So yeah, you can write now this same thing what we have written over here. Now if I consider this multiplication sigma into delta H, and delta H is delta of del U1 upon del X1, delta of del U1 upon del X2, delta of del U1 upon del X3, and then delta of del U2 upon del X1, delta of del U2 upon del X2, delta of del U2 upon del X3, then delta of del U3 upon del X1, delta of del U3 upon del X2, delta of del U3 upon del X3. So if you look at this multiplication and take the trace of this, that is multiply and then take sum of the diagonal elements, you will get actually know exactly this quantity. So you can write finally, I am going to write that as, so this delta W sigma is equal to integration over the reference volume into J we have already got, and then this I can write trace of this sigma into delta H into dV naught. So this I am denoting by sigma. Now you can, let me directly put the arrows. So this is sigma and this is your delta H. So we can write it like this. And now this will be possible. You can actually expand and look at the proof yourself. So this I can also write delta integration over reference volume J times trace of. So this I can write also because sigma is anyway symmetric. So sigma transpose into delta H into dV naught. And this you can also see can also be written as integration over V naught J into trace of sigma into delta H transpose. All will give you the same thing, delta H transpose into dV naught. So I think I want to stop here, and I know if you have any doubts and questions you can ask. Yeah. So hello, are there any questions, doubts? So finally, we are going to look at this quantity what I have derived, delta W sigma, that I'm going to write in the, this is written in the reference configuration, but still we have the Cauchy stress and delta H. So we want to bring in here, the first Taylor-Kirchhoff stress tensor and delta F, and similarly we want to bring in the second Taylor-Kirchhoff stress tensor and a variation of Green-Lagrange strain tensor D delta capital E. So those proofs I will look into in the next class. So yeah, if you have any doubts and questions, you can ask. Anybody, any doubt, any question? Hello, am I audible?
Hello, sir.
Yeah.
Sir, actually, I want to ask another question, that how can I get the contact details of TA of this course?
The TA is Sumit Kumar. He's a PhD scholar. So if you in the IIT mail server, if you write Sumit Kumar, you will see. You can get his email ID.
Sir, one of my project mate tried looking for details, but there are many names with that.
Okay, so I will send an email. I will send one email giving his email ID. Okay, I will do that.
Okay. Sir, actually, I'm asking, like yesterday, I asked that the result is not converging. So when we are going into the plastic region, so in one step it is converging. Like for the first time when it goes into the plastic region, two of the Gauss points are coming in elastic and two are in plastic. For that step, the result is converging. But for when the next load increment it goes into the plastic region, the whole element, it doesn't converge. So we wanted to connect to a TA and like discuss this thing in detail.
So yeah, I will send you that email. I think I will send the email.
Okay, sir. Thank you, sir.
Yeah. Any other question, doubt, anybody on this, whatever we discussed? Okay, so if there are no questions and doubt, I'm stopping. Thank you all for your attention. Please go through what I have discussed, and if you have doubts and questions, you can ask in the next class.